Below you is Port Sutton near Tampa, Florida. Below you is Port Sutton near Tampa, Florida. This is Comco's first full-scale composite fuel production plant, capable of mixing coal pulverized to ultrafine particle size with residual fuel. Coal arrives at Comco's plant by railroad hopper cars. Pre-crushed coal to -3 inch is received from 18 massive coal tunnels. This elevating conveyor belt subjects the arriving coal to magnetic separation, where tramp metal is removed prior to fine grinding. The coal then continues on up a series of conveyors and is ultimately delivered to stockpile. The coal is stockpiled in the open by means of a radial stacking conveyor. Coal recovery consists of a front-end loader, which recovers the coal from stockpile as needed, and transports the coal to a feeding hopper, which is equipped with a bottom vibrating output feeder that regulates the flow of coal into the primary crushing circuit located to the left. An elevating conveyor drops the coal into this Williams number 240 reversible impactor, where a primary reduction to -1/8 inch is achieved. After crushing, the coal drops by gravity into the bottom conveyor, which then elevates the coal into storage bins. This overall view shows the feed hopper to the left, elevating conveyor to the crushing tower, and the product elevating conveyor shown to the right. The Williams impactor has reduced the coal to 90% -1/8 inch at the rate of 60 tons per hour. The coal then drops into these storage bins shown in the background, prior to feeding to the Williams pulverizers shown in the foreground. We are now looking at a gravimetric feeder which is feeding each pulverizer at a rate of 7.5 to 10 tons per hour, resulting in a total production in excess of 30 tons per hour. All startup, shutdown, and operating functions are monitored by this Williams analog control panel. Automatic and manual mode operation is optional. This is the feed control gauge that displays the mill's bed depth of material in inches of water column. Next to it is the display of the 500 horsepower drive motor amperage. This gauge gives the mill's rotational speed, or RPM. The mill speed is adjustable utilizing this trim pot. This overall view of the Williams micronizing pulverizer shows the main air circulating fan and its drive to the left, while below the pulverizer we have the power drive scheme. This is the standard torque 500 horsepower drive motor coupled to a Lewis Alice water-cooled electric variable speed clutch, which in turn is coupled to a full right-angled gear reducer. By utilizing standard components, Williams has designed an isolated drive system which cannot be contaminated by coal and which is readily accessible for system maintenance. Air-to-water heat exchanger is provided for the electric clutch. Here, the dissipated heat energy is removed from the closed-loop cooling system. ash coal up to 40% and hard-to-grind pyrites and tramp metal are periodically unloaded down this reject chute, as simulated in this picture. Leaving the drive system, we now approach the pulverizer's airlock feeder. This feeder runs continuously and provides an even bed of coal as called for by the differential pressure controller, located by the control panel. At the same time, it prevents the egress of oxygen into the system. Processing 15 to 20 tons per hour of coal, the Williams micronizing pulverizers are grinding the coal to a fineness of 98% minus 325 mesh. Of course, part of the overall design parameters were to allow for ease of maintenance. Shown here are the oversized access doors located in the pulverizer cover. What you just heard was the startup of the 500 horsepower motor. The motor starts unloaded as the clutch is not as yet activated. By manually adjusting the clutch trim pop shown earlier, variable speed can be achieved to optimize the pulverizing conditions. Operation of the pulverizer in an open condition as shown is not recommended. There is always a chance of fire or explosion. Normal operation with the door closed is with an oxygen level of 8 to 9%. Complete access and removal of the pulverizing journals can be made through the access door. The system air system is comprised of the main fan, shown to the left, which causes the fine ground coal particles to be elevated from the pulverizer to the spinner separator. This is an active classifier and has a remote variable speed drive that allows accurate classification of the micron coal. Once sized, the micron coal is then conveyed out of the spinner separator and over to the cyclone separators, where the coal is centrifugally removed from the air. The cyclone separators cause the coal to disassociate from the airstream and discharge by gravity out the bottom outlet. Adjacent to the cyclones is a baghouse that is utilized to remove substantially all coal particles from the airstream that have escaped the cyclone separator. This baghouse product then is screw conveyed over and airlocked into the cyclone product discharge. Contingency planning dictated that besides the control of the system oxygen content, provision should be made for a possible malfunction. To that extent, explosion venting has been provided on all cyclones and ductwork. Discharging from these cyclones at a rate of 15 to 20 tons per hour drops below into a tank where residual oil is mixed to produce a fuel-oil mixture called COM economic. This plant is designed to produce 3,000 barrels of coal oil mixture per day. The ultra-fine, 98% passing 325 mesh particles, is comparable to talcum powder for fineness. These ultra-fine coal particles remain suspended in the oil after once being mixed, removing the need for chemical additives. Other advantages of this ultrafine particle size is the minimized erosion and abrasion of the customer's boiler system and equipment, as well as the reduction of boiler ash-related problems. Zero it out. Yeah. All right. Now how much you gonna shake in there?
About 7 grams would be good.
6 or 7 grams. That's 0.5. There's 6 there. And put it on your Alpine. Is constantly checked, and the spinner separator particle sizing system has proven to be very accurate and will hold the product size within a half of 1%. The heart of the pulverizing system is the Williams patented inert gas system, comprising of the main fan to circulate the relatively inert gas, the exhaust fan used to remove the steam-laden gases, and the baghouse used to clean the gases prior to discharge, and the air heater used to generate the drying and inert gases, and the panel-mounted oxygen analyzer used to monitor and alarm the system on excess oxygen. This then is the Williams combination number 6 oil or natural gas air heater. This heater generates 6 million BTUs per hour and allows simultaneous drying and grinding of wet coal. This system will dry wet coal with up to 15% free moisture. An analog temperature recorder is supplied so as to control and monitor the system temperature. Furnace outlet temperature is also monitored and alarmed. By burning the oxygen out of the air conveying system, a relatively inert hot gas is developed. The heat is utilized to dry the coal while it is being pulverized, and the inert gas provides a safe operating system. This system is being operated at 7% oxygen level, which will prevent any explosions or fires. And so the Port Sutton plant has demonstrated that coal oil mixture can be handled much the same way as oil. Here we see a 20,000 barrel tank barge being loaded for shipment across Tampa Bay. To Florida Power's Bartow 125 megawatt generating plant, which has been retrofitted to burn COM. To date, over 200,000 barrels of COM have been burned with great success and right on target. Idaho Supreme Potato Company has installed an innovative type of coal conversion system. Shown here is the company's over-the-road truck, which delivers the coal to the plant. The coal is discharged from the bottom dump trailer over a grizzly and into the receiving pit. 2-inch by 0 bituminous coal is used, containing 13,000 BTUs per pound and up to 8% H2O.
Show me some of the coal. Does it all go through?
Some of it, the oversize is kept on top of the grizzly, and the undersize falls through the grizzly, into the chute, and down into a screw conveyor.
Where's the screw?
Screw conveyor.
Oh, okay. The screw conveyor goes from there.
Draws the material up into the screw conveyor, and then drops it down. Past a magnet.
Where's the magnet? Show me the magnet.
Magnet's right here. Material passes over the magnet.
All right.
Drops into the bucket elevator.
All right.
Which brings the material up to the top of the bin.
Okay.
Storage bin holds about 400 tons.
400-ton capacity then represents slightly more than 4 days operating time, as we will be burning at a rate of 4 tons per hour in the boiler. After unloading, the coal truck begins its round trip back to the coal mine. Completely enclosed and neatly installed inside the lower portion of the 26-foot diameter Butler storage silo is a complete coal pulverization system, including feeder, Williams DF52 pulverizer, cyclone collector, main circulating fan, and pulverizing coal transport fan. The wind box of the DF52 pulverizer can be seen through this access door. We are now inside of the coal storage silo, and shown is the Karman vibrating discharge feeder, which is located at the bottom of the coal storage bin. This feeder prevents bridging and ensures continuous coal flow to the Ramsey Waybelt feeder. This is a close-up of the feeder inlet section.
It passes a gate.
Coal passes down this conical section through the coal shutoff gate, which is in the open position, enters the Waybelt feeder at this point, travels at a variable rate of speed depending on demand, is discharged heavily goes down, chute below the floor down. Discharge from the Ramsey volumetric weight feeder travels vertically down to the inlet of this screw conveyor, which transports the coal into the DF52 at this point.
This is a cross-section of the Williams DF pulverizer and its main skid-mounted drive assembly.
125 horsepower, 1800 RPM Toshiba motor. It is directly connected to a Falk right-angle gear reducer with a 15.12 to 1 reduction ratio.
Okay.
The mill motor is controlled by a variable frequency AC controller. This is an extension of the automatic grease lubrication system, which puts grease into the main mill bottom bearing at this point.
The pulverizer cross-section shown here has a large access door through which journal assemblies are easily removed for yearly maintenance. Shown here are 6 DF52 pulverizers under construction at the Williams Bonne Terre plant in Missouri.
Okay, bring it around so that we can see the lubrication system.
Unlike bowl mills, the Williams DF mills have no springs. Crushing force is derived by centrifugal force. The journals are free to roll over uncrushables. For purposes of demonstration for this picture, the pulverizer access door has been opened and the pulverizer operated at a slow speed. Note, faster operation would be hazardous. Capacity adjustment is achieved by varying the central shaft rotational speed. Each Williams DF mill is equipped with a tramp metal throwout chute. By opening this large gate, removal of hard-to-grind materials is accomplished. This is done periodically, normally into a wheelbarrow.
Here it is. There's a piece of metal in there. It looks like it
Bring it.
jumped off. And
Get
here's
it
some
on the ground.
slag. Okay, so it accumulates at the bottom.
Williams uses an active classifier we call a spinner separator, which is located directly above the DF pulverizer as shown here. Because of the dynamic classifier design, sieve analysis of the pulverized coal remains at 95% minus 250 mesh at high or low loads.
This is a steam coil type
The pulverized coal is conveyed out of the coal pulverizing area into the building that houses the boiler and coal burner.
The Cohen burner.
The coal travels past this coal shutoff valve and enters the Cohen burner, which is located on the front of the boiler. The burner is designed to fire coal, gas, or oil. The burner and burner management system were supplied by Cohen. This then is the Cohen dual air zone scroll feed multi-fuel burner. The flame pattern can be changed by adjusting the louver assemblies located at the core air zone and the annulus air zone. The overall view shown here is of the coal storage silo on the right, the boiler and boiler room in the center, and the baghouse and fly ash hopper to the left. The design of the Bigelow Type A water tube boiler makes for easy conversion from oil or gas to a solid fuel boiler. This cross-section of the boiler pressure parts shows the flue gases passing through the furnace section and then splitting at the back of the boiler so as to travel back through the convection banks and again join above the steam drum to discharge vertically to the economizer. This is the back end of the Bigelow Type A open bottom Model 4224A-82 boiler, modified by Holman Boiler Works. The furnace volume is 2,760 cubic feet and has a total heating surface of 7,300 square feet. The boiler is rated at 70,000 pounds of steam per hour at 140 psi when firing coal. The design heat input is approximately 95 million BTUs per hour. By looking in the observation viewport, we can observe the coal flame at various boiler demands. This flame is at 15% demand and has a 10% gas igniter.
Okay, take it up.
At 25% demand.
We are now at 25% boiler demand.
This represents 1 ton an hour of coal.
It is burning entirely in the length of the cone.
The boiler has now been brought up to a 50% load.
This then represents 2 tons an hour of coal. In this view from the roof level, you can see the baghouse and exhaust fan for the boiler, which are in operation. Note how clean the exhaust gases are. This installation was required to meet the most stringent clean air requirements. The boiler is presently operating at 100% demand. Because this system was started up in their off-season, the entire 70,000 pounds per hour of steam had to be vented to atmosphere as there was no plant demand. This is the 100% coal flame at full boiler demand. The coal has been pulverized to 95% minus 250 mesh. And this is a sample of the baghouse ash as collected from the Micropulse baghouse. It is 92% minus 37 micron and contains only 1.6% free carbon. When in normal operation, this steam will be used to process and dehydrate 1 million pounds of potatoes daily. The conversion from natural gas to coal is presently saving Idaho Supreme potatoes over $125,000 per month.
Okay.
This rotor can easily be turned by hand, as you can see, with very little effort. Showing that the bearings are functioning well and lubricated.
Is that direction in which it normally rotates?
It rotates in the down-running side like this. This is the rear edge of the breaker blower.
Okay. And how many tons would you think that have gone through this now? How many tons an hour is this thing rated
It's
for?
around about 600. It's been running somewhere around 600 tons an hour, and I would say easily there's been 60,000 tons through here.
One right in front of you. There it is. What's that, Carson? That won't burn so well, will it?
Correct. Lots of wear on it. Now, is there any grizzly in this that we dump this stuff into? That size? What size is a grizzly? 12 by 12. 12 by 12 grizzly.
Thank you.
looking at is the dump hopper for the primary raw material. Home is loaded in at this point.
You're looking at the dump hopper. It's a 260-ton hopper, which feeds 2 ROM feeders raised at 200 tons per hour. That continues on up the reclaim belt, which is good for 350 tons an hour. With your magnet, after it passes through your magnet, any material that the magnet doesn't pick up, we have a Tektron device with a reject gate on it that can be triggered by anything as small as a chewing gum wrapper. It will deflect a diverter gate to dump out on the ground here in case some piece of metal gets past that magnet. It would then be picked up by the Tektron metal detector and rejected out the side before it continues on up the transfer conveyor to the top of the fuel silo, which is 2,650 ton capacity.
Okay, out of the reject chute then comes the tramp metal. Would you hold up some of the tramp metal for me?
Goes up 2 redundant crushed fuel conveyors to what's known as the South Transfer Tower. And the South Transfer Tower is where the primary sample is taken from the primary crusher. Then leaves there and goes up the 2 plant feed conveyors into a 55-ton 110 ton, I'm sorry, surge bin.
section and superheater section. Got the cyclone here, seal pot.
Where the open
That's the upper combustor. Yeah, our refractory comes down to about here. There's about 16 inches of refractory on the lower water. And then all up here is a big heat transfer area.
So most of the heat transfer is taking place in this portion?
Yeah.
Up in this area here? This is just a combustor section here?
Right.
The heat transfer and where you're going into the oils and the steam? Make it.
We got our superheater elements right in this area here.
Ash pit, which we dump the ash out of the ash cooler that you value after its condition. Here we dump it in the mounds. You can see the mounds. We have to keep those mounds leveled down to a thickness of approximately 2 foot every day. The dozer operator will go down and knock down the piles to a thickness of about 2 foot.
Runs are used to transport the pulverized coal to each burner. Each pipe run has a coal flow cutoff valve, which is driven by an air cylinder. These valves are always closed when the pulverizer is shut down. This Foster Wheeler burner is equipped for coal, number 6 oil, and gas fuels, reducing the turbulence in the inner annular region nearest the fuel while directing the major portion of the air to the outer annulus, lowers the flame temperature and NOx.
The back wall of the burner where the burners are located. Okay. This is the
The new number 1 and 2 power boilers at International Paper Company are designed to meet the mill requirements from the firing of pulverized coal, fuel oil, and bark. They are capable of obtaining their maximum continuous rating when fired with coal or fuel oil alone or in combination with bark. Bark is recovered from the debarking operation at the mill.
Truckload of bark that just came into the mill yard. We buy our bark from contractors. And this bark is put on an unloader that lifts the truck up and dumps it into this traveling bark feeder, which continuously feeds the bark belt. And leaving the bark belt, it takes on off and goes up towards the crusher to take care of any big stuff that's in the bark.
Bark conveyor number 1 is equipped with a self-cleaning magnet to remove ferrous metals. The birch's bark then drops down beneath the magnet onto the bark disc screen. Here the larger pieces are conveyed over the screen and into the bark crusher. The smaller chips drop through the screen and go directly to bark conveyor number 2. The bark crusher is a Williams number 580 no-knife hog. It employs the hammer mill principle of size reduction, where material is crushed by impact between a series of rotating hammers and a fixed anvil. Crushed bark leaving the crusher falls onto the bark conveyor number 2 and goes on to the stacker reclaimer system along with bark that comes from the woodyard. Adjacent to the bark handling facility is the coal unloading system, where coal trucks are received and unloaded.
As you can see, our trucks come in by, our coal comes in by trucks. This is a bottom dump, hydraulic dump truck. He's backing over the Grizzly, which is known. These are 10 by 10 squares that the coal falls down into a stainless steel chute, so there aren't any sparks. The bottom hydraulic gate is open. He's putting the coal down into that hopper. This is a 2-hopper truck. It holds approximately 30 tons of coal, and it takes about 15 minutes to get the hoppers empty.
We have a 10-inch by 10-inch Grizzly here for the trucks to dump over. Occasionally we can get some large-sized coal that's going to come in, and we'll go through the Grizzly.
Okay, would you knock some of that coal around so we can see what it looks like?
Coal is coming up this tube that you see here, and then right alongside the silo we have a bucket elevator. The coal dumps into the bucket elevator and it carries the coal to the top of the silo, and this is our storage area.
This silo is used as a short-term storage tank to replenish the boiler coal bunkers. It has a capacity of 1,200 tons.
Bottom of this coal silo, and you have a vibrating feeder on the bottom of this thing, and it goes onto a coal belt and transfers over to a belt number 2, which brings it on up to the power plant. Number 2 coal conveyor, which is enclosed in this tube going up to the power plant. As you'll see further on up in your picture, it goes to a transfer tower, and you'll see another tube heading towards the power plant.
Coal conveyor number 2 is the longest of the coal conveyors. It is a belt-type conveyor 36 inches wide and is traveling at a constant speed of 350 feet per minute. Magnet number 4 is located near the discharge of the coal conveyor number 2 at the transfer tower. It is designed to remove any tramp metal that comes from the unloading system or the coal silo, each coal bunker. These bunkers are 18 foot in diameter and 48 feet high, and each bunker has a capacity of 134 tons.
We have air blasters located on the side of the cone to knock the coal loose inside of the bin. Down on this side, we blaster. Then we come down to the bottom of the cone, and we have a rack and pinion slide gate above the feed chute going to the stock feeder on the floor below. We're now located on the floor below the feed bin and the manual slide gate that we showed you just a few minutes ago. Here we see the discharge bin coming from that slide gate to the back end of the stock gravimetric feeder. The stock panel, local panel, and we are watching the feed rate going into the pulverizer. At the present time, the feed rate is increasing. It is going up to 4.2 to 4.3 tons per hour capacity. Now the feed rate is up to 4.4, 4.5, and climbing. Is a totalized delivery, which is 2,196,400 pounds delivered totally through this feeder. In this section of the feeder is where the weigh cell is located that gravimetrically weighs the coal as it crosses the belt. Here we see the drive mechanism for the stock feeder, and up here we have a float switch that is checking the level of the coal on the belt.
The float switch located over the 24-inch wide belt can be seen at the top of this picture. Each feeder discharges into a Williams DF52 pulverizer. These pulverizers each have a maximum capacity of 14,770 pounds per hour and are driven by a 125 horsepower variable speed drive. This is the sound of the coal as it enters the feed pipe and drops into the pulverizer.
Now, underneath the pulverizer, and I will now let you listen to the pulverizer, sound of the pulverizer. From where I'm standing, there's not much noise coming from the pulverizer itself. Now we will go down and I will let you listen to the gearbox as it is in operation. As you can listen here, most of the noise level that we hear underneath the pulverizer here is coming from the gearbox itself and not from the pulverizer. It is running very quiet.
Shown here are the 6 Williams DF52 pulverizers. Operation of the DF system is completely automatic, utilizing the ROM computer system. The gravimetric feeder shown earlier is preset to the boiler requirements, and the ROM also sets the DF mill speed required to do the grinding. The grinding journals are free to swing out under centrifugal force to grind the raw coal. Being free to pivot, the rolls automatically assume the proper position for grinding, and there are no springs to adjust. This then constitutes an air-to-coal ratio of 1.7. Once ground to size, the coal is air swept out of the mill by air bustles or wind boxes that surround the bottom of the mill. At the present time, the coal fineness is being set and ground at 87% minus 200 mesh, and the capacity of each mill is 14,770 pounds of feed per hour. Full load amps on the 125 horsepower motor is 136 amps.
Located on the opposite side of the drive skid package for pulverizer number 3, boiler number 2. Up here, we have the discharge spout, which comes out at the bottom of the pulverizer for discharging tramp metal, pyrites, things of this sort that collect in the bottom of the pulverizer.
came up the conveyor. It was delivered to number 2 pulverizer. You can see here that this metal got in underneath the plow, as did this, and could have caused severe damage if not detected. This all wound up in the metal trap, was exhausted out. At this time, we weighed this up, and there is 15 pounds of metal that came out of the bottom discharge of the number 2 boiler, number 3 pulverizer. As you can see, these were nuts and bolts that were cut loose from the conveyor.
Airflow from the FD fan is divided into 2 streams. 65% of the air is blown through the steam coil and the tubular air heaters for use as combustion, over fire, and primary air to the coal pulverizers shown here. The temperature of this air is approximately 505 degrees Fahrenheit upon exiting the tubular air heater, having been subjected to heat transferred from the 60 psig steam. Tempering air is provided to maintain constant air temperatures to the coal pulverizers. Temperature sensing devices are provided at the outlet of each coal pulverizer's fan. These devices regulate automatic dampers, which allow sufficient tempering air in to maintain primary air temperatures at the established set point of 150-degree exit temperature. Shown here is the positive air shutoff valve, which is located next to an airfoil. The basis of the measurement of airflow is the differential pressure across this airfoil, and it controls the airflow damper. The raw coal delivered to this plant may and most likely will contain foreign substances. Much of this material can become a source of ignition in the pulverizer. Therefore, a steam deluge system has been added should a pulverizer fire be detected.
Frequency AC drive associated with the spinner separator. This unit is a GE variable frequency drive, and we use this to control the speed of the spinner separator. By controlling the speed of the spinner separator, we can control the fineness of the product leaving the pulverizer at the various loads.
Comes out of the union behind this flexible hose. Travels down the stem. And into the block.
This block, put your hand on it, right there. Now there's pistons in that block that move back and forth and distribute the grease, correct?
That's correct. Grease distributes and goes out of these hoses and into trunnion blocks.
Trunnion block.
Air also travels around the grease hose inside this pipe, comes down through behind the flexible hose and through a rotary air seal unit. The air then travels through these red hoses and enters into the journal via a check valve here and purges the seal area.
And where does it exit?
The air then exits from behind these flingers. Blow the dust away from the seal area.
Plows located ahead of each roller direct the coal upward and between the grinding rolls at the heavy alloy steel bull ring where it is ground to size. Once ground to size, the coal is swept out of the mill by the controlled airflow into the Williams adjustable spinner separator for final product size. Each pulverizer discharges into a Chicago blower coal exhauster. These exhausters are driven by 150 horsepower, 1200 RPM motors. One exhauster supplies 2 coal burners via 2 discharge headers. Shown here is the temperature sensor that is used to control the tempering air and the hot air damper, so that the outlet temperature here is 150 degrees Fahrenheit.
at this point to the burners. You have a switch that shows when the unit is open, and this one here shows when it is in by consent. The operator is opening up, indicating that it is now open, and these lines are now in service and ready for air and coal to be blown to the burner. Plus the burner pipe going up to the burners up on the upper level.
Number 1 and number 2 power boilers designed by Foster Wheeler Limited are capable of generating a combined continuous steam output of 850,000 pounds per hour at operating pressure and temperature of 1450 psig and 950 degrees Fahrenheit.
Okay, right here we have the Forney flame safety system, which is showing a coal fire in level 2 at this time, and another pulverizer in standby position on the upper level. Here the operator can take and call up a graphic on this particular pulverizer, and he can look at the whole system from the coal bunker, the feeder, down to the pulverizer. The feeder speed right now on this particular unit is running at 23%. The set point for the pulverizer speed control is set at 68.37%, and it's running at 68.49 at this particular time. The amps being pulled by the pulverizer motor are 68 amps at this time, and the primary airflow to this particular unit is 20,000 pounds an hour. The pulverizer temperature itself is 148 degrees, which is a little bit at the cool side at this particular time, because we're looking for our pulverizers to run between 150 and 160 degrees. System is doing. He has got this whole system on automatic. He is putting in 3.12 thousand pounds of coal an hour. His pulverizer differential is showing 5.21 inches. His spinner speed control on his pulverizer is 18.12%. His pulverizer speed control is running at 68.12%. He is on header pressure control, and this pulverizer is watching the header pressure, and it ramps up and down as his header increases or decreases. Right now it is holding the header at 1,452 pounds.
What information does the Forney system give you?
The Forney system tells us, shows us the flame. The operator can tell whether he has a flame. He also can call up the Forney system, which I'll do at this time, on that particular level for that coal burner, which is coal level 2. By depressing these buttons, and he calls up this system and changes the graphic, and it also shows a picture of the pulverizer system from the coal bunkers and the feeders on up, the coal valves. Now the standby one, which is coal level 1, will show you that only the spinner and the motor on the pulverizer and the exhauster is running with the coal valves open. All he will have to do in order to get that unit in service in a hurry, if he needs it, is to walk over and to push the coal feeder button and put it in automatic, and it automatically ramps up this pulverizer and brings it on up and puts it on the line, and he has almost an instantaneous fire.
product exits from the shredder building, it comes up to this diverter valve. And with this diverter valve, you can make a selection as to where the product will go. It can go on up to the cyclone, as shown here. Bottom line from the diverter valve, cause the product to be diverted over and go directly to the boiler. And the United States flag in the background. And that paper then traverses across this entire route, which is over 500 feet, and travels down and into a secondary fan, where it is then pumped up into the top of this cyclone and discharges down into Idaho Supreme Potato Company has installed an innovative type of coal conversion system. Shown here is the company's over-the-road truck which delivers the coal to the plant. The coal is discharged from the bottom dump trailer over a grizzly and into the receiving pit. 2-inch by 0 bituminous coal is used, containing 13,000 BTUs per pound and up to 8% H2O.
Show me some of the coal. Does it all go through?
Some of it, the oversize is kept on top of the grizzly, and the undersize falls through the grizzly, into the chute, and down into a screw conveyor.
Where's the screw?
Screw conveyor.
Oh, okay. The screw conveyor goes from there.
Draws the material up into the screw conveyor, and then drops it down past a magnet.
Where's the magnet? Show me the magnet.
Magnet's right here. Material passes over the magnet.
All right.
Drops into the bucket elevator.
All right.
Which brings the material up to the top of the bin.
Okay.
Storage bin holds about 400 tons.
400-ton capacity then represents slightly more than 4 days operating time, as we will be burning at a rate of 4 tons per hour in the boiler. After unloading, the coal truck begins its round trip back to the coal mine. Completely enclosed and neatly installed inside the lower portion of the 26-foot diameter Butler storage silo, is a complete coal pulverization system, including feeder, Williams DF52 pulverizer, cyclone collector, main circulating fan, and pulverizing coal transport fan. The wind box of the DF52 pulverizer can be seen through this access door. We are now inside of the coal storage silo, and shown is the Carman vibrating discharge feeder, which is located at the bottom of the coal storage bin. This feeder prevents bridging and ensures continuous coal flow to the Ramsey Waybelt feeder. This is a close-up of the feeder inlet section.
It passes a gate. Coal passes down this conical section through the coal shutoff gate, which is in the open position. Enters the Waybelt feeder at this point. Enters the belt at approximately this level. Travels at a variable rate of speed depending on demand. Is discharged. Discharge from the Ramsey volumetric weight feeder travels vertically down to the inlet of this screw conveyor, which transports the coal into the DF52 at this point.
This is a cross-section of the Williams DF pulverizer and its main skid-mounted drive assembly.
125 horsepower, 1800 RPM Toshiba motor. It is directly connected to a default right-angle gear reducer with a 15.12 to 1 reduction ratio. The mill motor is controlled by a variable frequency AC control. This is an extension of the automatic grease lubrication system, which puts grease into the main mill bottom bearing at this point.
The pulverizer cross-section shown here has a large access door through which journal assemblies are easily removed for yearly maintenance. Shown here are 6 DF52 pulverizers under construction at the Williams Bonne Terre plant in Missouri.
Okay, bring it around so that we can see the lubrication system.
Unlike bowl mills, the Williams DF mills have no springs. Crushing force is derived by centrifugal force. The journals are free to roll over uncrushables. For purposes of demonstration for this picture, the pulverizer access door has been opened and the pulverizer operated at a slow speed. Note, faster operation would be hazardous. Capacity adjustment is achieved by varying the central shaft rotational speed. Each Williams DF mill is equipped with a tramp metal throw-out chute. By opening this large gate, removal of hard-to-grind materials is accomplished. This is
And here's some slag. Okay, so it accumulates at the bottom.
Williams uses an active classifier we call a spinner separator, which is located directly above the DF pulverizer as shown here. Because of the dynamic classifier design, sieve analysis of the pulverized coal remains at 95% minus 250 mesh at high or low loads.
This is a steam coil type heat exchanger, which has the transport air passing through it. The hot gas then enters the inlet of the mill at approximately 200 to 250 degrees Fahrenheit. Hot air travels
material comes down.
Material comes down and enters the rotary valve, which then enters the coal transport system. And at this point, the transport air is taken from the system and goes upward to the inlet of the transport air fan, which is on the second floor. This is where the transport air is delivered into the inlet of the constant volume transport fan. Discharge and makes this elbow. And at this point, the constant speed rotary valve, which delivers the coal into the transport system, which then enters this pipe and leaves the storage bin pulverizing area.
From the transport air fan discharge, the pulverized coal is conveyed out of the coal pulverizing area into the building that houses the boiler and coal burner.
The Cohen burner.
The coal travels past this coal shutoff valve and enters the Cohen burner, which is located on the front of the boiler. The burner is designed to fire coal, gas, or oil. The burner and burner management system were supplied by Cohen. This then is the Cohen dual air zone scroll feed multi-fuel burner. The flame pattern can be changed by adjusting the louver assemblies located at the core air zone and the annulus air zone. The overall view shown here is of the coal storage silo on the right, the boiler and boiler room in the center, and the baghouse and fly ash hopper to the left. The design of the Bigelow Type A water tube boiler makes for easy conversion from oil or gas to a solid fuel boiler. This cross-section of the boiler pressure parts shows the flue gases passing through the furnace section and then splitting at the back of the boiler so as to travel back through the convection banks and again join above the steam drum to discharge vertically to the economizer. This is the back end of the Bigelow Type A open bottom Model 4224A-82 boiler, modified by Holman Boiler Works. The furnace volume is 2,760 cubic feet and has a total heating surface of 7,300 square feet. The boiler is rated at 70,000 pounds of steam per hour at 140 psi when firing coal. The design heat input is approximately 95 million BTUs per hour. By looking in the observation viewport, we can observe the coal flame at various boiler demands. This flame is at 15% demand and has a 10% gas igniter.
Okay, can you ask him to take it up?
At 25% demand.
We are now at 25% boiler demand.
This represents 1 ton an hour of coal.
It's burning entirely in the length of the cone. The boiler has now been brought up to a 15% load.
This then represents 2 tons an hour of coal. In this view from the roof level, you can see the baghouse and exhaust fan for the boiler, which are in operation. Note how clean the exhaust gases are. This installation was required to meet the most stringent clean air requirements. The boiler is presently operating at 100% demand. Because this system was started up in their off-season, the entire 70,000 pounds per hour of steam had to be vented to atmosphere as there was no plant demand. This is the 100% coal flame at full boiler demand. And this is a sample of the baghouse ash as collected from the micropulse baghouse. It is 92% minus 37 micron and contains only 1.6% free carbon. When in normal operation, this steam will be used to process and dehydrate 1 million pounds of potatoes daily. The conversion from natural gas to coal is presently saving Idaho Supreme potatoes over $125,000 per month. Installation of a petroleum coke system at Union Camp's number 2 lime kiln, located at Prattville, Alabama, is a major step for this mill and the paper industry in general. Although petroleum coke has its disadvantages, the advantages outweigh the potential problems. Petroleum coke should offer a viable source of lime kiln fuel into the future, as will be shown. Approximately in the center of the pad is an opening through which coke will be introduced into the system. The opening is approximately 9 feet by 10 foot and is covered by a grizzly which has 8-inch openings. Using the front end loader, the coke will be either pushed or dumped through the grizzly to the reclaim hopper below. The number 1 conveyor is the first of 3 long transport conveyors. This conveyor is 136 foot long and rises to a little over 36 feet. The belt is 24 inches wide and is driven at a speed of 250 feet per minute and discharges into the crusher. Just ahead of the head pulley is a magnetic separator that will pick up any pieces of steel that might be mixed in with the coke. This is to protect the crusher, which follows next. The magnet that is being utilized is a Stearns Model 25A electromagnetic cross-belt conveyor. Metallics drop down this chute for subsequent removal. Since the coke will be purchased unprocessed, we may receive pieces up to 6 inches in diameter, and a pulverizer cannot accept anything larger than 1 inch in diameter. Therefore, a crusher has been provided to ensure that no oversized material will be fed to the pulverizer. This shows a typical sample of the pre-crushed coke. The number 2 conveyor is the second of 3 long transport conveyors. The conveyor is 844 feet long and rises approximately 78 feet. The belt is 24 inches wide and is driven at a speed of 250 feet per minute. The conveyor is loaded from the crusher and discharges to number 3 conveyor. A considerable amount of attention has been given to minimizing dusting with this conveyor system. All conveyors have been provided with dust-tight covers, and all other openings have been provided with seals. In the discharge chute of number 2 conveyor, a 10-inch suction line has been provided for a dust transfer fan. This is number 3 conveyor, and it is 70 foot long and rises approximately 15 feet. The belt is 24 inches wide and is driven at 250 feet per minute. A storage silo has been provided at the hot end of number 2 lime kiln that has a capacity of 123 tons. This is slightly in excess of the requirements for 1 day when burning maximum coke. The silo is 14 foot in diameter and a straight wall height of 25 feet. Load cells have been provided so the weight of the silo and hence its contents can be determined. The weight or indication of how much coke is in the silo will be determined on a control panel.
And into their stock gravimetric feeders. As material comes on, it's weighed and conveyed down the length of the conveyor, down into our chute that goes into our rotary air valve.
Okay, tell me what you're doing now.
Okay, I'm weighing the sample. So I'm going to put the sample in the top lid.
A portable moisture analyzer is next used to determine the raw coke moisture content. First, a sample of coke is weighed in a balance. Next, carbide will be introduced into the pressure vessel so that when it mixes with the moisture, acetylene gas is formed. The pressure of this gas produces a direct reading of coke percent moisture.
Together, tighten the lid, then mix it. Let's see, I've mixed the reagent and the moisture sample together. And the gauge tells us we have 15% moisture, surface moisture.
The coke will next be dried from the 15% moisture down to 0.3% moisture as it is being ground to 90% minus 325 mesh. Coke offers several advantages for use as a lime kiln fuel. The primary advantage is cost savings when compared to natural gas and number 6 fuel oil. The high heat content of petroleum coke also adds to its attractiveness. Coke usually runs about 14,000 BTUs per pound. Shown here are the kiln's heat exchangers, where the 600-degree Fahrenheit drying gas is obtained for the Williams DF pulverizer. This heat is required to dry the 15% surface moisture from the coke during the grinding operation. The hot gases exit from the top of the firing end of the number 2 kiln and are conveyed through this 24-inch diameter duct past a tempering air damper. This damper allows fresh air to enter at this point if the system temperature goes too high. Both the system temperature and the volume of air are controlled by the Williams 200 series computer, which will be explained later.
The air enters by way of this 24-inch diameter pipe into our wind box. As the air comes into our wind box, it circulates around and comes through what is known to us as porthole liners, or porthole openings in the bottom of the mill. The air enters, it rises, bringing the material with it. The lighter material passes through our classifier and out through the top.
Comes out of the union behind this flexible hose.
Alright.
Travels down the stem.
Okay.
And into the block.
This block, put your hand on it, right there. Now there's pistons in that block that move back and forth and distribute the grease, correct?
That's correct. Grease distributes and goes out of these hoses
Okay.
and into trunnion blocks.
Trunnion block.
Air also travels around the grease hose inside this pipe, comes down through behind the flexible hose,
Okay.
and through a rotary air seal unit.
Alright.
The air then travels through these red hoses
Okay.
and enters into the journal via a check valve here and purges the seal area.
And where does it exit?
The air then exits from behind these flingers
Okay.
to blow the dust away from the seal area.
Directly above the DF52 pulverizer is the spinner separator. Through the speed of this device, the coke particle size is accurately controlled to 90% minus 325 mesh.
Okay, this is our mill drive. The mill is driven by a 150 horsepower motor that has an AC variable frequency drive on it. It's connected into our spoke coupling right angle gear drive.
By varying the speed of the mill vertical shaft, the output of the pulverizer can be made to match the input of the feeder through the Williams 200 series computer.
This is the Williams System 200 computerized control system. All the instrumentation you see here is the metering devices, temperature control, manual speed pots, and handheld data terminal.
Please open the case and take that out. Okay, leave the case door open and just pull it out for you. Alright.
Okay, the next thing we want to monitor will be differential pressure.
Alright, while you pull up the differential pressure, we'll take a look up here as to what it's actually doing. And you're going to pull up monitoring.
It's varying between 6 inches and 6.4 inches.
Alright, could you hang that back up and let's take a look at the control panel, and then we'll go under the control panel to look at the computer.
The system is set up so the first thing in sequence that you turn on will be the control power and the computer power together.
Show me the computer.
Okay, the computer is located down in the lower right-hand front corner of the control panel. The computer consists of 3 boards.
Okay, show me the boards. One there.
CPU board, analog input, and discrete I/O, and analog output. You will notice there's a very large accumulation of dust inside this panel. That is because this panel is open on the bottom to the operating environment outdoors where the kiln is located at. These boards are all conformally coated to be able to work within these conditions.
All right. Okay, what do you got there in your hand?
This is a sample of the product coming to the burner from the pulverizer.
Right next to the... Okay, put a little more on there. And would you smell? That's what I was looking for. Now, what is the fineness on this?
Okay, the fineness here is 88% minus 325 mesh.
Once the material is fine enough, it travels out the classifier, out the top of it, across through this 18-inch diameter pipe, travels into the exhauster. Once it reaches the exhauster, it's then picked up, transported directly up to the kiln by way of this 18-inch diameter pipe.
I'm presently standing alongside the Cohen combination fuel rotary kiln burner. Burner is designed to burn a number of fuels and is presently firing petroleum coke, pulverized with a sustaining natural gas fire. The petroleum coke enters the kiln through this 18-inch pipeline, passes through the 18-inch safety shutoff line, down and into the center of the burner. approximately 450 degrees Fahrenheit and enters through this ductwork controlled by this damper and enters the burner around the outer circumference of the coke stream. Coke stream itself passes down along the center line of the burner and into the firing area of the rotary kiln. The burner is presently firing approximately 100 million BTU per hour, with between 80 and 85% being petroleum coke. The remainder being...
Now is on the tip of the burner. What you should be able to see is a black area called the fuel plume. This is an area of unburned coke just prior to ignition. You may also be able to view streaks in the black coke plume, which are jets of natural gas that are being used to sustain the combustion of the coke. At the end of the black area or plume, ignition occurs and is extremely radiant in color, similar to an oil fire. The fire itself appears to be well defined.
We're looking at the number 2 lime kiln, and lime is producing at about a rate of 250 tons a day. The lime's approximately at the hot end 2200 degrees. The cold end temperature is about 560 degrees.
Installation of the petroleum coke system for the number 2 lime kiln is a major step for this mill and the paper industry in general. Although petroleum coke has its disadvantages, the advantages outweigh the potential problems. Below you is a new 150,000-pound 1500 psi fluid bed combustor, as manufactured by ASEA Stahl. Run-of-mine Wyoming subbituminous coal is received at the job site by railroad hopper cars and dumped through this 6-inch by 9-inch grizzly into the collecting hopper below. It is then elevated by this 18-inch drag conveyor and bucket elevator to the top of this 30-foot diameter, 96-foot tall, 220-ton storage bin. The coal, containing up to 27% free moisture, is recovered from the bottom of this silo by this live bottom bin and weigh belt feeder at a rate as called for by the fluid bed combustor. It then drops down into a Williams number 15 by 20 single roll crusher, producing a 2 by 0 inch product. The 2 by 0 coal is then elevated by a 12-inch drag conveyor to the top of the Williams number 43 DF roller mill located on the outside. When preparing fuels for circulating fluidized bed combustors or fluidized bubbling bed boilers, the Williams DFM mill has certain advantages. Number 1, surface moisture for coal of up to 27% can be handled without derating. Number 2, fines are pre-stripped from the feedstock by hot air, thus reducing over-grinding and subsequent carbon loss from the combustor. Hot gases entering at the wind box surrounding the mill cause a partial fluid bed inside the pulverizer. The computer operating the DFM mill controls the speed of the mill so as to grind at a rate matching that of the feed system. Slow speed grinding does not generate excess fines. The main vertical shaft is driven by a remote right-angle Falk gearbox coupled to a standard 50 horsepower motor. The motor in turn is connected to a variable speed drive, resulting in a grinding system with infinite turndown. This 50 horsepower motor will grind 22,000 pounds an hour of coal. The main fan for the air system is also connected to a variable frequency drive, so that the distributive control computer can adjust particle size and fineness upon demand. More airflow results in a coarser product, thereby allowing fuel size flexibility on demand and minimizing carbon loss. The outlet air temperature is controlled to approximately 120 degrees Fahrenheit, while the inlet temperature is approximately 350 to 400 degrees Fahrenheit, thus drying the 27% free moisture in the coal down to 9% and transporting the finished product to this cyclone, where the solids are removed from the airstream. This system is known as semi-direct firing system, in which the fuel is pulverized in an air-swept DFM mill and then is separated from the air in this 9-foot diameter cyclone. The fuel discharges at the bottom through a 14 by 14 rotary airlock and is picked up by 2 PSIG conveying air from a primary blower and is conveyed directly to the Aciastol boiler. For the purposes of this video, a product sample is obtained. As you can see, the system is under 30 inches negative pressure. Normally, a 7-inch cyclone is attached to this pickup probe, but the coarse fuel requirements would not allow the older design to work efficiently. Instead, the probe tube is capped to prevent the egress of air, and a representative sample is obtained. This Wyoming subbituminous coal, with a feed moisture of 27%, has been dried to 9% moisture and ground to 99% minus 1/4 inch, with only 2.3% minus 90 micron, and an average D50 particle size of 1,350 microns. 2 psi transport air now conveys the prepared fuel to the Aciastol distribution center inside. Here, distribution of the coal and air is made into 10 separate 3 1/2 inch diameter lines. Each of these lines then traverse under the boiler to its appointed fluid bed area, and is again redistributed into 4 separate 1 1/2 inch diameter lines that feed up into the bubbling bed above. This then is the Aciastol bubbling bed boiler, rated at 150,000 pounds of steam per hour, with a steam pressure of 1,500 psig. This boiler provides steam for this plant, and by means of a separate turbine generator, manufactures 9.8 megawatts of energy for internal consumption.
Now change the graphic over to show everything in color. basically what the graphic shows. Standard boiler. Outlet temperature of the pulverizer. You have a classifier, we know the classifier speed. Differential pressure. Inlet, air temperature, airflow. Mill speed. Mill amp. Meter span. Okay, this is our distributor plate. In here you see material, which is limestone. The material falls through a feed chute down on this deflector plate onto the distributor plate. The distributor plate then slings the material off the outer edges down in. Here we have the journal assemblies, which rests on top of a spider. The grinding action takes place down here between these grinding rolls and what we refer to as a bull ring.